All right, so I'm going to start off by taking a look at section 6.4, which is on graphing, the last 4 trig functions that we haven't looked at yet. We're not going to be doing any sketching really by hand. We did a lot of that when we did sine and cosine. So we're going to focus mainly on how do we do it on the calculator, and then some other things on the calculator as well. So let's think a little bit about tangent. And this is going to help us to figure out what it looks like. Does anybody remember how you can write tangent as a fraction? It's a fraction of 2 trig functions divided by each other. Another way to think of it would be when we did unit circle. Does anybody remember when we did sine? That was equal to what letter? Yep.
Y.
Sine was y. And what about cosine? What part of the coordinate was cosine? Yep.
X.
That was x. And now, does anybody remember what tangent was? Yep.
It was Y over X.
It was y over x. So if you think of it that way, tangent is really what divided by what? Yep.
The sine of X over the cosine of X.
Yeah, it's the sine divided by the cosine. Now, just a little bit of a refresher on what sine and cosine look like. Okay, sine, just the first cycle, looks like that. That's 0, pi over 2, pi, 3 pi over 2, and 2 pi. So that's what sine looks like. And cosine looks like this. Again, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Just kind of put the labels wherever I had space to put them. So, does the graph of sine ever cross the x-axis? Anything, Ashley?
Yeah.
Yeah. How about the graph of cosine? Does that cross the x-axis?
Yeah.
Yeah. Now, when a graph crosses the x-axis, what's the y value? Anywhere that a graph crosses the x-axis, yeah?
0.
0. Okay, so what we're saying here is the graph of sine and the graph of cosine is 0 at various points. Well, there's tangent, sine over cosine. What would happen in any fraction if you try to divide by 0? Because cosine definitely is 0. We just looked at the graph. It crosses the x-axis at different points. And what happens if you try to divide something by 0? Yeah?
0.
If you have a 0 in the top, it would divide out to 0. But if you have a 0 in the bottom, yeah?
Undefined.
Undefined. Okay, we'd have an undefined value. And when you graph, if something is undefined, that usually means you have an asymptote. So the graph of tangent is going to have vertical asymptotes, which means it's not like sine and cosine. Sine and cosine, you can put your pencil down and you can just trace. You can't do that with tangent because the asymptote is going to break the graph. Okay, so that's the first thing to just kind of think about tangent a little bit. It's not connected. It's repetitive, like sine and cosine. There's a pattern to it, but it's not a connected pattern. So, let's think about when tangent would be 0 and when it would be undefined. So tangent would be 0 if you make the top 0. That's the only way that a fraction can ever be 0, and that's what Tyler said earlier. 0's in the top. Then, no matter what, you're going to get 0 as an answer. So the graph of tangent will be 0, or I could say the graph of tangent will cross the x-axis when the sine crosses the x-axis. So sine and tangent cross the x-axis at exactly the same spots. Now, tangent will be undefined or have a vertical asymptote whenever you try to divide by 0. So that'll happen when the cosine is 0. So wherever the graph of cosine is 0, you're going to get a vertical asymptote. All right, so let's look at our graph. Sine is 0 at 0 and pi, and 2 pi, and 3 pi, and 4 pi. It's 0 at every multiple of pi. So I go to my graph of tangent. Let's mark that. It's going to cross the x-axis at 0, 1 pi, 2 pi. So my graph of tangent is going to go right through all 3 of those points. But it's going to be broken up by asymptotes. I'm going to have a vertical asymptote whenever the denominator is 0. So now let's look at cosine, and let's look at where cosine is 0. Can somebody tell me the first spot where cosine is 0? Yeah, okay. Pi over 2. What's the next spot? Yep. 3 pi over 2. And then 5 pi over 2. And 7 pi over 2. So we're going to get vertical asymptotes at all those pi over 2s. 1 pi over 2, 3 pi over 2. Basically odds. Odd multiples of pi over 2. So let's put those in. We have an asymptote pi over 2. 3 pi over 2. I'm just going to draw that one, because those two asymptotes will give me one section of tangent. Now I'm going to draw what happens in between the two lines. Whatever happens in between those two lines is exactly what would happen between those two lines. Okay? Pattern is going to repeat itself. So let's put in tangent and let's check the table. Okay, I'm doing it in radians. I know I'm in radians because I don't see any degree marks on any of my labels on the x-axis. Calculator's in radians, so that's good. And let's do what we always do. Let's check a value just after, let's call this asymptote number 1. And let's check a value just before asymptote number 2. Don't check the asymptote, that's going to say error. But check something very close to it. So, what's really close to pi over 2, but a little bit bigger? Pi over 2 plus 0.01. Just a little bigger. So let's do pi over 2 plus 0.01. I don't even know what that is. I'm just going to type it in. But I know it'll give me a value just a little bit to the right. And my y value is negative 100. So it's way down here. Now, let's check an x value that's just a little bit smaller than asymptote 2. Asymptote 2 is 3 pi over 2. So let's just subtract a really small amount. Just take 3 pi over 2 minus 0.01. So I'm trying to see where my graph is going. Is it going way down? Is it going up? That's what I'm trying to figure out. And I'm up at 99.99. So it's going up very high. So all those 3 dots have to be connected, and it's kind of it's a curve. So it's going to look something like this. It's going to stay very close to that dotted line, but then it has to go through that point. Then as it keeps trying to go to the right, it gets stopped by that asymptote. And that's what the graph of tangent looks like. And that is one full cycle, what you're looking at right there. Here is a second cycle. Kind of like that. That's a second cycle of tangent. So let's graph. And let's just set my window from 0 to, well, I'll go to 3 pi. That's the edge of my, well, it's close to the edge of my screen. on the smartboard. 0 to 3 pi, and hit graph. So I didn't draw everything. There's a little bit more because you're seeing part of another cycle. There technically would be a part right there, which I didn't sketch, and then there'd be another part coming up right there, and I stopped it at 3 pi so you wouldn't see any more. You know, that's what tangent looks like. Now, let's see if we can figure out what the period is. This is one cycle. What's in that green box? From pi over 2 to 3 pi over 2. Does anybody remember what is pi over 2? If we change that to degrees. Yeah, that's 90. Yep. And how about triple pi over 2? How much is that? Yep. 270. That's the beginning and the end of one cycle of tangent. What's the difference between those two numbers? Yeah. 180. That's the cycle of tangent. It has a 180 degree cycle. Does anybody remember what the cycle for sine and cosine was? It wasn't 180. Remember, yeah?
360?
It was 360. So sine and cosine naturally cycled every 360 degrees. Well, tangent naturally cycles every 180. That's the period of tangent, pi. And we also kind of have to think about these asymptotes and which asymptotes belong to which cycle. It's kind of like armrests, like in a movie theater. Right? You can't, if we want to share equally, this is what we have to do here. Maybe not in real life. We have to do that here. So every cycle has to have the same number of asymptotes. You can't have one cycle have two of them on each side of it, and then the guy in the middle doesn't get any armrests. Everybody has to get the same. So what has to happen is each cycle has one asymptote. So if I was thinking about it, like that second green box is the next cycle, it doesn't matter how you think of it, but I would think of it as the asymptote on the left as belonging to the graph that comes after it. So asymptote number 1 belongs to this graph. Asymptote number 2 belongs to the next graph. And then asymptote number 3 would belong to this one that I started drawing. Okay, but each cycle only has one asymptote. And again, if it's confusing, just think of like the arms in a movie theater. You can't have one cycle with 2 and the other cycle with 2 and the one in the middle with none. That it doesn't work. They all have to have the same. All right, so that's what tangent looks like. And cotangent, well, I'm not going to go through it in as much detail, but cotangent is when you take tangent and you flip it. So now what's going to happen is everywhere that there was a 0, that's going to become an asymptote. And everywhere that we had an asymptote, that's going to become a 0. So if we go back and look at it, we had an asymptote at pi over 2. In cotangent, pi over 2 is now a 0. In cotangent, there's an asymptote at pi. If we go back to tangent, pi is a 0. Okay, so all the zeros in the asymptotes switch places, and the curve goes the other way. Okay, same deal here. That's one cycle. These continue up and down forever. And every cycle has one asymptote in it. Okay, but very different from sine and cosine. They're not continuous. You have to lift your pencil every time you want to draw another cycle. What else? This has the same period length as tangent. The period length is pi, or 180 degrees. I think I write that on the next page. Okay, any questions on that? All right. So that's what I've been saying. The period of tangent and cotangent is pi. So what does that mean? That means if you add pi to an answer and take the tangent of it, you're going to get the same thing. Let's look at an example. Let's take the tangent of, just pick a number, 3. That's what I get. Now, if I take the tangent of 3 and I add 1 cycle length, all that that's going to do is, just to pretend, like let's say 3 is right up here. It's a horizontal line at 3. That was the first answer that I got. If I add pi, I'm going to get this answer. The answer is how high the point is, but it's at exactly the same height as the one before it. So if I take 3 and add pi, I get exactly the same answer. And if I take the tangent of 3 plus 2 pi, I get the same answer again. Now I get this one. So adding and subtracting multiples of pi will always give you the same answer when you're dealing with tangent, okay? Not sine and cosine. So this is the property that I just showed you guys. If you take the tangent of something, or you take the tangent and you add any multiple of pi to what you started with, you'll get exactly the same answer. And what's pi in degrees again? How much? Yeah. 180. So if I had to think about taking the tangent of something that was really big, like let's say I had to take the tangent of 3,600 degrees. Well, 3,600, that's a big number. I can't really think that through in my head. But I could take 3,600 and I could subtract 180 from it as many times as I wanted. And subtracting 180 isn't messing up the answer. There we go. But eventually, it's going to get small enough that I'm probably going to recognize what it is. Well, that's easy. It's the tangent of 0, which is something I can find a lot easier in my head than 3,600. So it's just like with sine and cosine. You could add or subtract 360. Well, with tangent and cotangent, you could add and subtract 180, which is really just half of 360. So we've learned how sine and cosine have transformations. Vertical stretch, vertical shift. And we've done that with every function we've studied so far. Well, for tangent and cotangent, the transformations work exactly the same as they always have. Now, if we had just done sine and cosine, like Monday, Tuesday, Wednesday, and we were doing this lesson on a Thursday, I would assume most people would just remember the transformations. But we did them before break, so I think it might be good to just quickly remember what they are. Okay, it's the ABCD that I always use. And what does A do? Actually, you know what? So I can go left to right. Let's start with C. What type of transformation would C be?
A vertical shrink or stretch.
Yep, that's a vertical stretch or shrink. Depends if it's a number greater than 1. That causes a stretch. So I'm gonna write it that way. So vertical stretch could be a shrink if it's between 0 and 1. What if C is a negative? What would that cause the graph to do? Yeah.
Reflection over the y-axis, or no, it's the x-axis.
Yeah, over the x-axis. Okay, C would be a vertical reflection, and when you flip it vertically, that's over the x. How about B? What type of transformation is that? It's multiplication like C, but now it's on the inside. Yeah?
Horizontal shrink or stretch.
Yep, that's your horizontal shrink or stretch, which with Trig we call a period change. Okay, again, that's your horizontal stretch. Or if you technically stretch something by a half, it's really a shrink. So that's B. How about A? A and D are both addition. They could be subtraction. Doesn't have to be addition. But what is A going to do? Yep, baby.
Horizontal shift.
That's your horizontal shift.
Up and
So that will shift it. And in trig, we call that a phase shift. That's your horizontal shift. And D, what's D going to do?
a vertical shift.
Yep, that's your vertical shift. So those transformations are the same that we've looked at all year. Any questions on those? So I might give you an example and just ask you to identify, the transformations that are happening. I don't think we said this, but if B is negative, that's a horizontal reflection. Just like if C is negative, it's a vertical reflection. I know we said that, but B could be negative. What about if A is positive? Which way does that shift the graph? I know it's horizontal, but I need a little more specific. Tyler?
Left.
Yeah, left. And if it's negative, it's right. What if D is positive? Which way does the graph move? Jake?
Right.
Which way?
Right. Okay.
Well, that would be what we just said about A.
Oh, did you say
D.
if D is positive or negative?
Positive.
Then wouldn't it move to the right? The side of the Oh, up.
Up. Yeah, D's vertical, so that would be up. And if it was negative, it would be down. A is your left or your right. All right, so we had a formula to figure out the period of sine and cosine if we modify it. And the formula is 2 pi divided by the number in front of x. That's the number that changes the period. Well, with sine and cosine, it was 2 pi over b. In general, the formula is the natural length of the cycle over b. For tangent and cotangent, the natural length is pi. Okay, and what I want to give you now is a chart that kind of summarizes where the asymptotes are for tangent and where they are for cotangent. I want you to leave 2 extra lines in the chart because I'm also going to tell you where the asymptotes are for secant and cosecant. But I just want to start with tangent and cotangent. Okay, so this is a summary of all the asymptotes for the trig functions we're going to study today. It's going to have 4 rows in it. So leave enough room. I'm only going to give you 2 right now. But for tangent, your first asymptote is at pi over 2. That's what, if you go back and look at the picture, that was the first one. And then it will occur every cycle. So if you do a transformation, how do you figure out what the new asymptotes are going to be? Okay, that's what we're going to do in a minute. But the first step in figuring out new asymptotes is to make sure you know the old asymptotes. Even though we haven't done it, you can probably guess what this part is explaining. That's explaining that the asymptote is going to repeat every cycle. Okay, but we'll talk more about how to find that in a minute. I haven't done that yet. What I'm really focusing on right now is just the originals. Okay, for cotangent, your first asymptote that you come across that's not negative is 0. It's not positive either. It's not negative. So that's the first one you come across. And again, that asymptote will repeat every cycle. And again, I would leave yourself about as much space as you just had there. Again, I'm going to give you 2 more things in a minute. But I want to go back now that I just explained this. Any questions on why those are the first 2 asymptotes you hit? Cotangent and cotangent. Okay. So now, how do we find the new asymptotes? Because those are going to move, right? If you shift them, if you do anything horizontally, those 2 asymptotes are going to move to a different spot. If you do something vertically, doesn't matter. Like if you shift up and down, that's not going to move the asymptotes. If you stretch up and down, doesn't move them. But horizontal stuff will. And think about where all your horizontal stuff is. Let's go back for 1 second. It's right here. Those are your horizontal shifts and your horizontal stretches. So A and B are the only 2 things that can mess up the asymptotes, that can slide them around. C and D won't. So C and D have no effect on the asymptotes at all. Just the A and the B. And that's why when we want to find the new asymptotes, all we really need to know is 2 things. Where did they start? And we know where they started because I just gave you a table. So go to your table. Look up where the original asymptotes were. So this comes from your table. Step 2, set that asymptote that you found in the table equal to the argument. What's the argument? This part in the red box. That's the argument. So set the original asymptotes equal to the argument and solve. That will tell you where the new asymptote is. Now what step 2 does is it tells you where 1 asymptote is. But that's all you need. You just have to tell me where 1 asymptote is, and then tell me that that asymptote repeats every cycle. So this is from step 2. And then we put plus the period times in. Okay, we'll go through an example of that. But that table that I gave you, that's going to be really helpful to doing step 1. Find all asymptotes in 1 period. Just go to your table. Okay, so Let's see. So let's find the period. And I thought I did one with asymptotes. Maybe that's after. All right, let's find the asymptotes here too. So let's find the period of that. And then let's describe the asymptotes. And then we'll do a sketch. All right, y equals tangent 2x. Can somebody remind me, what is the formula to find the period of tangent? Yep.
Pi over b.
2 pi over b. And what's b in this case?
2.
2. So, did you say 2 pi over b or pi?
Said pi.
Oh, pi, okay.
I don't know why you said 2.
So, the tangent in this case is pi over 2. So, find the period. That's the period. Now, let's practice finding an asymptote. The first step in finding the asymptote is to know the period. Well, we already have that. So, the answer to my asymptote is going to look something like this. I'm going to find an asymptote, and then I'm going to tell that it repeats every cycle. What I don't know right now is what to put here. I need to figure this out. So, for tangent, can somebody remind me what's the first asymptote that you hit in the graph of tangent? Yep.
Pi over 2.
Pi over 2. So we're going to take pi over 2. It has nothing to do with this other pi over 2, just a coincidence. But so pi over 2 is the first asymptote that we hit in tangent. And the directions say, set that equal to the argument and solve. Here's your argument, 2x. Now think about what that 2 is going to do. It's a horizontal stretch. Technically, it's going to compress it by a factor of 2. So what that means is, let's pretend that these are asymptotes. They go up and down forever. But if you compress them by a factor of 2, what's going to happen, well, is this. This one doesn't even move. Pretend that it's at 0. It's just going to stay at 0. But everything else is going to get squished in closer to it. They still go up and down forever. I wish I could just stretch it one way, but I can't. But they're all going to get squished. So let's see if this asymptote gets squished. So set the original asymptote equal to the argument and solve. How would I get x by itself there? Chris?
Divide both sides by 2.
Yep. And I'm just going to think of that as multiplying each side by a half. So now, my asymptote is at pi over 4, which definitely is squished. It's half of what it was, so it got squished. And that is what you put right here. So your new first asymptote is at pi over 4, and that asymptote is going to repeat every cycle. In this case, that's every 90 degrees. So now, they want us to graph that and show 3 full periods, or 3 full cycles. You can say period or you can say cycle. It means the same thing. So if one cycle is pi over 2, how much is 3 cycles? Yep.
Would it be 5 pi over 2?
That would be 5 cycles.
Please excuse this interruption just at this time. Thank you.
So you have the right idea, but that's just too many. Yeah?
Maybe 2 pi.
2 pi? So what's 1 cycle again? Someone remind me, what's 1 cycle? Yeah?
Pi over 2.
So 3 cycles is when you triple. What's pi over 2 tripled? Yeah?
3 pi over 2.
3 pi over 2. So if they want us to show 3 cycles, you need to set a window on your calculator that is 3 pi over 2 units wide. That's kind of like saying set a window that's 10 units wide. There's lots of ways to do that. 0 to 10, 1 to 11, 10 to 20, 90 to 100. Those are all 10 units wide. So you pick however you want to set it to be that width. The easiest way I think to do it, if it has to be 3 pi over 2 units wide, let's go 0 to 3 pi over 2. Let's type in our graph. And by setting it that wide, we should see exactly 3 tangent cycles. We might break a cycle. That's okay. If we break one, which we did, we broke 1 in half. So that's 1 1/2, 2 1/2, plus another half is 3. That is 3 cycles. But we did what they said. That's fine. So find a viewing rectangle. I would say this viewing rectangle worked fine. That was 0, and this was really 3 pi over 2, which it'll just change to a decimal for you. Don't have to worry about y min and y max too much, because these graphs go up and down forever. So any questions on finding that viewing window? Okay. All right, so this is a kind of like just an identify which one is which. You'll have a question similar to this on the test. So one of these is the graph of 2 tangent x, and the other one is 5 tangent x. Can you tell me which one is which? So it requires you to know what the 2 and the 5 are kind of doing. And then imagine doing that. But what are the 2 and the 5 doing? What kind of transformation? Yep.
It's a vertical stretch.
It's a vertical stretch. So basically, which one of these looks like it was stretched vertically more than the other? Yeah.
The graph on the left.
The graph on the left. So if you take something, say it looks like this. I mean, you can see right now that it's got a pretty sharp curve in the middle. If I take that graph and I start to stretch it vertically, well, I just want to stretch it vertically. I don't know why it's not letting me. I just want to stretch it one direction. Well, if I stretched it in just one way, it would start to straighten out. That's what would happen. So the curve in the middle would start to get less pronounced the more I stretch it. Usually I can stretch on either axis independently. If I make a circle, I can stretch it either way. That's all I wanted to do. So I take that. Oh, there we go. Perfect. So there it is. You can see the curve really pronounced. And the more I stretch it vertically, the less pronounced the curve gets. So this is the 5 tangent x. And this is the 2. Questions on that? Okay. All right, so now, the last thing I want to finish filling in this table, but I want to talk a little bit about secant and cosecant first. This is what the graphs of secant and cosecant look like. They have vertical asymptotes, just like sine and cosine. But the question is, how many per cycle? And remember, we have to keep the same number of asymptotes in every cycle. Here is 1 cycle. What I just put a box around That is one cycle of secant. How many asymptotes do you think belong to that cycle? If you're not sure, just imagine another cycle right next to it. And that has to have the same number of asymptotes as the red box. They all have to have the same. Yep.
2 asymptotes?
It is 2. It's 2 per cycle. So if I was describing which ones belong to the blue box, how I would think of it, I would say asymptotes 1 and 2 belong to the box in blue. Asymptotes 3 and 4 belong to the red cycle. Asymptotes 5 and 6 belong to the next cycle after that. Okay, but there are 2 asymptotes per cycle. And cosecant looks similar to secant because sine and cosine look very similar. The only difference between sine and cosine is their phase shifts of each other. If you remember, sine and cosine are 90 degrees apart horizontally. That's exactly what these are. If you took this U shape and you slid it to the right 90 degrees, it would look exactly the same as cosecant. Now, do we have a button for secant or cosecant on the calculator? So how do we put secant in if we don't have a button for it? Anybody remember how we type it? Yeah?
Isn't it 1 over secant? I think.
Well, we don't have secant as a
Oh,
button.
I mean, sine.
Which one is 1 over sine?
Yeah, secant. Would be 1 over sine. Oh, I know. I know it's 1 over sine.
Anybody remember which one that one is? The 1 over sine? Yeah, that is one of them. Yep,
1 over sine is cosecant?
that's the cosecant. And 1 over cosine, that's the secant. Okay, so that's how we have to type it in on the calculator. So like if you had to type in something like 4 secant x, the way you type it in is 4 times 1 over cosine. Or you could write 4 over cosine. You could combine it all together. So I've just kind of highlighted where the asymptotes are. Again, pointing out to you that there are 2 per cycle, or 2 per period. What else? If you get confused and you can't remember where the asymptotes are, well, secant has asymptotes wherever the cosine is 0. Cosecant has asymptotes where the sine is 0. So just go back and look at those 2 graphs and see where the sine or the cosine is 0. Okay, to find the period of secant or cosecant, it's the length of the original cycle divided by b. Since secant and cosecant come from sine and cosine, they have the same period as sine and cosine. So most of the time, if you want to find the period, it's 2 pi over b. The only ones that use pi over b are tangent and cotangent. I put absolute value around b because technically b could be a negative number. When we studied sine and cosine, it never was, but it could be. And if it is, you want to ignore it because the length of a period can never be negative. Period length is always a positive number because it's length. You can't measure something and have negative length. All right, so now we know the first 2 asymptotes in a secant graph and the first 2 asymptotes in a cosecant graph. Let's add those to the last 2 rows in that table And now we have a full table for all our asymptotes. So we've got tangent and cotangent. And because secant and cosecant have 2 asymptotes per cycle, you have to describe both of them. Technically, there's a way to describe them all in one. It's a little more complicated. So even if it's not the most efficient way to do it, we'll describe them separately. First 2 asymptotes you come across for secant, pi over 2 and 3 pi over 2. That's where your cosine is 0. And the first 2 asymptotes for cosecant are 0 and pi. That's where the sine is 0. Okay, does everybody have the chart? All right, we did asymptotes for tangent. Let's do one for secant. And then the next one is cosecant. I'll probably skip it because they're very similar. Domain, range, period, and asymptotes. Well, let's start with the period. That's probably the easiest one. And you need the period to do asymptotes. So you probably want to do the period first. All right, what's my formula to find the period of secant? David?
2 pi over b.
Yep, 2 pi over b. And what's b in this case? So when you look for b, where is b?
Horizontal or
Well, is it out in front?
no.
No, that's c. So where are you looking for b? It's always, what's the location of it?
That's the end.
Well, at the very end, that would be like a plus or minus would be a vertical shift, if you mean like all the way on the right. Yeah?
Inside the parentheses.
And where inside the parentheses?
To the left. Like the first one.
The first one? So it's always right next to, yeah, the x. It's the coefficient of the x, which in this case is what? Okay? 1. So this problem doesn't have a period change. So it's just 2 pi. Now, we have to describe our asymptotes, but that's going to be easy because there is no change to the asymptotes. The asymptotes here are the originals. So what's the first asymptote that we come across for secant? And if you forget, what I'm thinking in my head is I'm like, okay, secant is 1 over cosine. Where does cosine hit the x-axis? That's what I'm visualizing in my head. Yep.
Pi over 2.
Yep. And
3 pi over 2.
and 3 pi over 2. And then we have to put plus the period times n, and that describes it repeating every cycle. So these are the asymptotes. Let's look at range for secant. Okay, if we just erase these, it might be a little easier to see. And zoom in. Okay. Does that graph go down forever? Okay. Does it go up forever? All right, so one more question. Does it hit everything in between? No, there's a gap here. So the range does go to negative infinity and positive infinity, but it doesn't hit everything in the middle. Does anybody think they can see how high that point is right there? How high up are we going? Yep.
-1.
-1. So this part of the range is from negative infinity up to -1. That describes from here up to there. So let's start with that. So range, negative infinity, up to and including, it does hit -1. Or, how would you describe this part of the range? From, yep.
1 to infinity.
Yeah, 1 to infinity. It's basically the opposite of the range of sine. Sine is everything between -1 and 1. This is everything not between -1 and 1. So 1 to infinity. And now lastly, let's look at the domain. Does the graph go left and right forever? You think, Chris?
Yes.
Yes. That pattern continues forever. Does it hit everything as it goes left and right forever? Like if I put a vertical line, would it miss spots anywhere if I drag it left to right? You think, Ashley?
Yeah, it would miss where the lines are.
Yes, it would miss all the asymptotes.
Yeah.
So the domain is everything except the asymptotes. Okay, that's how we can write it. So domain, all reals except the asymptotes. Now, if you get the asymptotes wrong and you say that, now you automatically have the domain wrong. So you could also say the domain is all real numbers except numbers of the form pi plus 2 pi n and 3 pi over 2 plus 2 pi n. You could say it that way as well. It's the same thing. Okay, so domain, range, period, and asymptotes. Okay, any questions on that? Now the next one was cosecant, and a lot of that would be the same. The period is the same. The range is the same. The domain, the wording is the same. But what would be different is the asymptotes. Instead of putting a pi and a 3 pi over 2, you would put pi and 3 pi over 2.
It was pi over 2.
and 3 pi over 2.
Yeah, I don't know if somebody said that and I wrote it wrong, but I just noticed that. Instead of being pi over 2 and 3 pi over 2, for cosecant, it should be a 0 and a pi. That's what you should have in the table. And that's the only thing that would be different if we did this problem. Okay, how about... All right, let's just find the period. And we'll do the asymptotes. I'm going to skip the graph. What's the period of cosecant 3x? Sarah?
Is it 2 pi over 3?
Yep, it's 2 pi over 3. So if I wanted to show a window that had 2 cycles in it, take that and double it. 4 pi over 3. Make your window that wide. Okay, what are my original asymptotes for cosecant? Yep,
I have a 0 and pi.
0 and pi. Actually, I'm going to do this off to the side. And what are we supposed to set each asymptote equal to figure out where it moves to? Because there is a transformation in this one. Yep.
The argument.
Exactly. Set each asymptote equal to the argument. And remember, if you have an asymptote at 0 and you squish it, well, it's like everything squishes towards 0, so it's going to stay right where it is. I mean, we can still set it equal to 3x and set that equal to 3x. And now to solve each of those, we're just going to divide each side by 3. So your first asymptote is x equals 0, and your second asymptote is x equals pi over 3. And how often are those asymptotes going to repeat? Yeah.
Would it be every cycle?
Every cycle, which in this case is 2 pi over 3. So you can add any number of cycles you want to the first asymptote or the second, and you will find another asymptote. Okay, so any question on finding the period and the asymptotes? All right. So the last thing is solving an equation on the calculator. Well, basically what this is going to be is finding an intersect. That's all. Now, let's just think about like the graph of tangent. It looks something like this. If you set tangent equal to a number, it's going to put a horizontal line somewhere. Doesn't matter what number you set it equal to, because tangent goes up and down forever. It is going to hit whatever number you set it equal to. If I start to put a horizontal line in there, how many times will it hit the graph of tangent? In general. Think about if you could graph tangent and zoom out forever. Yeah? Yeah?
Infinite.
Infinite, right? Because the graph of tangent is just going to keep repeating. If you put a horizontal line in here, it's just going to keep going. So the horizontal line and the graph hit each other infinitely many times. So what that means is if you can find a single solution, then that means you have infinitely many. How often do the answers repeat? From here to here is one cycle. There's your next answer. One cycle. The answers are going to repeat every cycle. So all you have to do is find one answer on the calculator and then put plus the cycle times n. And that shows me that it repeats every cycle. Right, so find a specific solution on the calculator. That's kind of like your starting asymptote when we do it that way. But we don't have a table for this. You have to do intersect and then figure it out. So find one solution and then put plus the period times n. And that'll tell me how often it repeats. When you find the solution here, focus on one cycle. Don't worry about what comes after one cycle. Whatever comes after one cycle is what's going to come at the cycle you're looking at. So just focus on one cycle. And I'll set my window to 1 cycle, so I don't have to see anything else. So if I was doing this problem, I would set my window just like that. Not worried about anything else. I know I'm going to find one answer, and I know it's going to repeat. I don't need to see it repeat. I know it's going to happen. Okay. All right. Finish up with this one. Find all solutions to cosecant equals negative 1.6. All right, so first thing, how do I type in cosecant on the calculator? Yeah.
1/9.
All right, so let's put in 1/9. Got that. What's going to go in y2? Jake?
Negative 1.6.
Negative 1.6. And now, I don't want to be looking at multiple cycles. I want to focus on one cycle. What's the cycle of cosecant? The length of it. Sarah?
2 pi over b.
2 pi over b, yes. And what's b in this case? Help us out. So what's b in this case? Okay.
Negative 1.6.
No, that's on the other side.
Oh.
So when we're looking for b,
Oh.
just look at the trig function and look at where the b is supposed to be. It's just 1.
Okay.
So there's no period change here. So it's just 2 pi over 1. It's just the regular period. So what I would do is set my window to go from 0 to 2 pi. It'll make it exactly 1 cycle on the screen. Perfect. So I should see 1 U shape and 1 N shape. That's how cosecant looks. If I see more than 1 U shape and N shape, something's wrong. That's perfect. So that's 1 cycle. Now, how am I going to find the 2 answers in this cycle? What am I going to do on the calculator? Chris?
Second calc intersect.
Yeah, second calc intersect. We're going to find the one on the left. All right, so that's one of my answers, 3.817. And now I need the one on the right. And that one is 5.608. And lastly, how often do they repeat? Each of those answers is going to repeat every, how often?
Wouldn't it be infinite? Or least?
Well, that's how many I'm going to have. Yes, there are infinitely many, but how often do they reoccur? Yep.
2 pi.
Every 2 pi units, every cycle. So my answers are going to be 5.608 plus 2 pi n and 3.817 plus 2 pi n. Technically, that should be approximate, not exact. And that's it. That's how you find your answers. All right, so as far as looking at graphing and having to use a graphing calculator, that's the only section this week we're going to need it for. Tomorrow and Wednesday, just a regular calculator will be fine. Any questions on that? All right, so that is the homework. So on page 352, 3, 6, 7 to 10, 13, and 15. 20, 28, 29, 31, 34, and 46 to 48. So tomorrow we'll take a look at that, and then we will look at our last section for the week, which is 6.1.